Hi guys, welcome to your Chapter 6, Lesson 1 Notes on Solving Systems by Graphing. By the end of the day, you'll be able to solve systems of equations by graphing. What does that mean? Why is this important? When are we going to use this in real life? Let's go backwards. Here's how we're going to use this in real life. Let's say that two professional downhill skiers, alternatively, you and your friend are skiing and racing down a hill. The first skier skis at a rate of 100 feet per second. Oh, rate. Nice. Okay, skier 2 skis at a rate of 110 feet per second. The course is 5,000 feet long. That's going to be our distance. We've got our rate. If skier, yep, that sounded right. If skier 2 starts 5 seconds after skier 1, will he win or will he lose the race? How do you know? Well, in order to, oh, hey, that was time. Nice. You'll remember one of our favorite formulas, distance equals rate times time. Here we know our rate and we know our distance, so I'm actually going to divide both sides by rate real quick. Divide by rate, so you see that the math works out. Now, what that really ends up doing is just wink, divide by rate on this side. So we get distance over rate equals time. Ooh, very exciting. Okay, anyway, so this is what we're going to use to help us solve this problem. Hopping right in, was actually super helpful. This picture. Haha, okay, we've got a hill. So person 1 starts and he's going 100 feet per second. Person 2 starts. After 5 seconds, wrong color, after 5 seconds and is going 110 feet per second down this distance of 5,000 feet. So we need to take our distance, we need to take our rate. Let's start with person number 1. So person number 1 travels a distance of 5,000 feet. Divide that by a rate of 100 feet per second. And that's going to come out to be 500 divided by 100, 50 feet per second. Our second person, not feet per second, 50 seconds. It will take him 50 seconds to get down this wonderful hill. It's a hill. Second skier does the same thing. He does 5,000 feet at a rate of 110 feet per second. That comes out to 45.45 seconds. And that difference, ladies and gentlemen, is a meager 4.55 seconds, which is less than 5 seconds. So yes, skier 2 will be a winner chicken dinner. Okay, that was a lot. If only there were a faster way to represent this. Well, guess what, guys? We can represent situations like this by using what is called a system of linear equations. But before we jump into big applications and word problems, I promise we're going to spend a whole day talking about applications like this, like when we're going to use this in real life. First, we're just going to practice with some very basic situations. Okay, so when you have 2 or more, we'll only ever have 2 in this class, 2 linear equations. Remember, these are liney guys. Whenever you have 2 lines, and we call it a system of linear equations. So it doesn't really matter what the equations are. Usually like 2x plus 1 and y equals negative x plus 5. And then we group them with a curly brace like that. And that's a system. Now remember how a line is defined. A line is defined by any set of x's and y's that make that equation true. Therefore, if you have an x and a y that makes both of these equations true, we call that a solution of the equation. Not just of the equation, but of the system of equations. So if you have any ordered pair, if you have any x, y pair that makes all of the equations, in this case both of the equations, true, we call that a solution of the equation. Isn't that great? For example, if we take y equals 2x minus 1, why not? And y equals negative x plus 5. This is our new system of equations. I'm going to just straight up tell you that the point that makes this true is the point 2, 3. Because when I plug in 2 for x and 3 for y, both of these equations are true. Don't believe me? Do you believe me? I mean, you might believe me, but I'm going to prove it to you anyway. I'm going to rewrite each of these equations by plugging in my x and my y in. Okay, let's check. Does it make our first equation true? Well, guys, are you trying to tell me that 3 is equal to 4 minus 1? That's true. Are you also trying to tell me that 3 is equal to negative 2 plus 5? That's true. Yay! Okay, so this point is a solution because it makes both equations true. My personal favorite way to do this is by graphing. We're going to use 3 ways. We're going to say there are 3 ways to solve a system of equations. We're just going to focus on graphing today. It is my personal favorite, but you have to be able to graph well, and it's not very precise. So how you do this is, since we're looking for the point that makes them both true, we're looking for the point where they intersect. That's our key idea. You're looking for their intersection. What point is on both lines? So let's go ahead and we'll graph this guy and this guy. So for our first graph, I notice it's got a y-intercept of 2, and the slope is 1. So I go up 1 over 1, up 1 over 1, up 1 over 1, all the way across, or I can just pick literally any of those points, connect them, and that's my first line. Awesome. Now let's graph the second line. That has a y-intercept of negative 2 and a slope of 3. That tells me to go up 1, 2, 3 over 1, 1, 2, 3 over, oh hey, how fun is that? 1, 2, 3 over 1, etc. Connecting, all these points. Amazing. Now that I have graphed both my lines, I want to figure out what point is on both of these lines. What point do they have in common? We're going to find some, I don't know, I'm struggling. We need to find some common ground here. Let's make this like orange. The point that's on both lines is this guy right here. Now, it doesn't look to be exactly on the point. It looks to be a little bit off. And that's why graphing fails just a little bit, because you have to graph it perfectly in order for it to work. But guess what, guys? The solution is this point where it appears to be at over 2, up 4. Now we can check it by plugging it into both of our equations. So let's check. Is it true that 4 equals 2 plus 2? Yay. Is it true that 4 equals 3 times 2 minus 2? Well, 4 is equal to 6 minus 2. So yay, it's true for both. So that's how you check your work. You need to plug your points into your equations to see if it's right. Now this system that we looked at, this has one solution because the lines intersect here. We call this we call this system consistent. It is a we're going to put 2 words in here, so give yourself some room. We call this a consistent system. Consistent. just like that, because they do intersect. Okay. So I'm going to, so what we're going to do is we're going to label these with some words, and then we're going to draw a sketch of a graph, and then we're going to describe what needs to happen for that to take place. Okay, so let's give ourselves a little visual reminder right here. Okay. So a consistent system means that there is an intersection. There are, in fact, two kinds of consistent systems. Let's see. If you have one line like this and another line, you know, like that, like we just saw, whatever, then they have an intersection, which is great. Say their intersection is like there. Sweet. We also call them, these guys will be independent. So they're consistent because they intersect, and they have different slopes, which makes them independent. Now there's another type of consistent system. Another type of consistent system is not independent. This guy is dependent. So when you have two lines that depend on each other, they're so close, they are literally the same line. So if you have the same line with two different names, that's a dependent system. We say this has infinitely many solutions because there's an infinitely many amount of points where they intersect. They are the same line. So all of these points along here, those will all make it true. So if you ever encounter two lines that have the same slope and they have the same y-intercept, therefore they are the same line. So whenever you encounter the same line, that's infinitely many solutions. That's a consistent and dependent system. There's one more that you can have. We've looked at different slopes. We've looked at same slope but same y-intercept. What happens if you have the same slope but a different y-intercept? When you have a different y-intercept, well, you know what happens when you have two lines that have the same slope but have different y-intercepts. We call those parallel lines. If you ever have parallel lines, they have no solution because there is no point that lies on both of these lines. There's not one point that makes them both true. That's impossible. You can't find any points in common. These guys have one point in common. These guys have infinitely amount of points in common. Great, huh? But these guys, they have no points in common. They have nothing in common except their slope. Aww. Anyway. So because this guy has no solution, it is not consistent. This kind is inconsistent. Cool. So now we need to classify and find the solution of each type. Down here. Okay, cool. So let's graph each line. I'm going to graph this guy first. Oh, that's in standard form. Excellent. So if I pretend that y doesn't exist for a while, I'm going to get that x equals 2. So I'm going to graph an x-intercept here. And if I pretend that x doesn't... Oh, wait. Yeah, that was right. Okay. No, that was wrong. If I pretend that this doesn't exist, I'm going to get negative x equals 2. So we got a negative x, 100%, my bad. And then, oh, I lost my intercept, negative 2. And then if I pretend x doesn't exist, we get 2y equals 2, so y equals 1. And there goes my blue line. Watch him as he goes. Whee! So we graphed our blue graph. Excellent. By the way, if you are not color coding, you should be labeling them with their name. Their name is their equation. So this guy would be 2y minus x equals 2. And then for my green graph, this is in slope-intercept form. So we're going to start at, oh hey, we're going to start at 1. That's so nice. And then we go up 1 over 2. Oh, wait, hold on. Up 1 over 2, up 1 over... You guys, guess what? They're the same line. Woohoo! Since we have the same line, this guy, what is the solution here? The solution is infinitely many. Infinitely many solutions. Because there's an infinite number of xy pairs I can plug in to make this true, to make the, oh, because they're the same thing. So what kind of system is this? This is a consistent system, and it's dependent. Oh wait, shoot, did I mess those up? Hold on 1 second. Let me actually look at my notes instead of getting super excited. Okay, anyway. You know what? I think I will just have to get back to you on their classification. So ask me again in class. Oh well, yep, I'm not gonna waste your time on a net puzzle with this. Okay. Carrying on. So when they are the same line, I know for sure they have infinitely many solutions. Okay. Now, let's go over to this guy. Let's graph each of these lines. Oh, here we go. Just kidding. I did switch them. Wait, no, I didn't. I'm right. I'm good. I'm good. You're right. Have confidence in yourself. Okay, anyway. So we graph our first line. We start at 2. We go up 2 over 1, up 2 over 1. Have a great day, and it's amazing. Graphing our line, graphing our line. Have a great time, graphing our line. Y-intercept is at -1. Guess what, guys? They have the same slope, so I'm just going to do this. Ta-da! Oh no, this has no solution. Why does this have no solution? They don't have any points in common. There's just no point to it, you guys. Sad. We totally could have seen this coming because look, guys. Same slope. Ah, they're parallel. Ah, man, this is an inconsistent system. I also recognize that phrasing is kind of weird because it looks very consistent, right? They're consistently doing the same thing, but you know it's more consistent? Literally being the same thing. So that's very exciting. Okay, let's do one more. When are we going to use this in real life? Well, I'm just going to jump forward and tell you anyway. Say you've got some alligators and they're growing at different rates, apparently, because this guy over here is growing at 1.5 pounds per month. This guy's only getting 1 pound per month. But that's okay, because he started out bigger. The initial weight and growth rate of each alligator shown. How many months did the alligators weigh the same amount? So what we can do is we can graph this. But, you guys, always use graph paper in your graphs, and we don't have graph paper here, so we're going to create some. Watch this. We're going to write down our key information. Okay. So we have alligator 1. We're going to write an equation for him. His initial weight is 4. So that means if we have y equals mx plus b, his starting weight is at 4. So that's our y-intercept is at 4. And then our growth rate is 1.5. We're going to do the same thing with alligator 2. His initial weight is 6 pounds, and his rate is 1 pound per month. Number 2. So for alligator 1, our equation is y equals 1.5x plus 4. And for alligator 2, our equation is y equals 1 times x plus 6. So now that we've got this key information, we can graph them on our graph paper. Oh, shoot, you guys. I didn't leave space for graph paper. Hang on to your hats. Ha! Okay. Add. I'm going to add a page. I should have added a page up here. Man, this is like the most struggle bus add puzzle ever. Add a page right in here. I'm going to go to this page, and I'm going to make him graphical. Sweet. Okay, let's make our graph. So the key to making our graph is knowing what our x's and y's are going to be, but we actually don't have a table. Okay, let's have this just be 1, 2, 3, 4. I'm gonna go every other because I'm getting kind of lazy. There, 12 months, that's a year. And then let's go that these are 2, 4, 6, 8, 10, 12, 14, 16, 20. All right, so here's the deal. We've got our x's, we've got our y's. Now we need to plot both of our lines. So alligator 1, let's make him blue. So we'll start him off at 4. And then he goes up 1.5 over 1. Oof, 1.5, you guys, that's the same thing as 3/2. So he's going to go up 3 over 2. He goes up 3 to 7 over 2 here. So his graph is going to stretch him out like this. Cool. And then our other alligator, let's make him brown. Why not? He's going to start off at 6, and he goes up 1 over 1 each time. We'll go up 1 over 1, up 1 over 1 each time. Ta-da! Okay. So when do they intersect? Well, they intersect at whatever point. Where did my point go? Here. What is that value right there? Well, that's when x equals 4. We can also figure out how much they're going to weigh. They're going to weigh, what is that, 10 pounds? But I don't think it asks us for how much they weigh. Did it? It just asked for after how many months did they weigh the same amount. And that was at 4 months. So they caught up. Oh, very nice. Cool? Cool. All right, when you're graphing, make sure to label what graph represents what line, somehow, whether it's through colors or by name. Remember the key definitions here. Look for your slope, look for your intercept, and that you want to find where the lines intersect. That will be your solution, because you want what point is on both of the lines. Hey guys, thanks for sticking with me. Have a great time on your homework.